in a batch culture of cells that is following the monod kinetics, the declining log phase lasts longer. It is a declining log phase that is lasting for longer period of time, and you have to determine the reason behind this when the cell culture is following the monod kinetics. So what is the declining log phase? So if we take this as the, so from the x-axis, if we take the time period, and y-axis if we take the number of cells, then in the initial case the growth was like this, and the later case the growth is like this. So here the second one has less number of cell produced in the same period of time. So like this. So to reach this number of cells, that the first one is taking less time and the next one is taking higher time to reach the same number of cells. So why that is happening? That you can get the reason from this monod kinetics. So the monod kinetics is just like the Michaelis-Menten equation that was for the enzyme and substrate concentration. So here it will be just like the mu equals to mu max. Now what is the mu? Mu is the specific growth rate, and mu max is the theoretically calculated the maximum value of the mu. So the mu theoretically can't go beyond the mu max. So depending on the equation is by Ks plus S. So this Ks is the Monod's constant, it is a constant, and S is the concentration of the substrate. So what is the mu? Mu is the specific growth rate, and from the definition you can get that dN by dt is equals to mu into n, the number of cells at that specific time. So depending on the equation, you can see that dN is the number of change, the change in the number of cells, that is the dN. So the mu is directly proportional with the dN. So if the mu is high, that means the number of newly produced cells will be higher in that case. So the dN is directly proportional with the mu. Mu will be high, that means the production is also high. And another thing is a dt that has a inversely proportional relation with the mu. That means if the mu is high, the time where the cell will be taken to be divided or to produce the new cells will be less, because the dt has a inversely proportional relation with the mu. Mu is high, that means to produce the same number of cells, the cell will take less time. And now let's come to the equation part. So the log phase, this log phase is the mostly exponentially growing phase for the cells. So in that case, depending on the equation, theoretically the mu should be reaching near to the mu max, because this is the only situation when the exponential growth is happening. The growth is too fast, that means the mu is in a high position. But when it will reach the stationary phase or the death phase, the value of the mu will be declined. But in the log phase, the mu's value should reach very near to the mu max. If theoretically from this equation we think the mu will reach to the mu max, that means the rest of the equation should be 1, and thus it comes, right? S should be equals to the Ks plus S. That means when the mu will reach the value mu max, beyond that it is not possible. That is in the peak. The mu value is in the peak. In that case, the substrate concentration should be equal to the substrate concentration plus Ks. which is not possible. Depending on this thing, we have to say the Ks should reach 0, which is not practically possible. We can think for it in the theoretical equations, which is not possible. So depending on this, we can get when the mu is too high, the Ks value should be too low, and the reverse will happen. When the mu value is low, the Ks value is too high. So now let's go to this part. In the first case, the mu was reached a high value. It got a high value that was very near to the mu max. But the next case, it is not able to reach till that. That means for the first case, the Ks was low, and for the second case, the Ks was high. So the declining of the log phase, that is lasting for longer due to the K's value when it is very much large. And from this equation you can get there is no relation with the mu m with the substrate. So it depends on the K's value only. So 1 and 2 is not possible and 4 is totally wrong. The third one is the answer. Continuous stir tank reactor means it is a continuous culture system. If this is the reactor, then the inflow and outflow will happen at a same period of time, and thus it will maintain a constant volume inside the reactor, and the cell will be in a continuous culture. So if that is the bacteria, then the growth will happen. So the lag, log, stationary, and like the death phase, everything will happen here. It is a continuous culture, and thereafter it is running at a dilution of 0.3 per hour. That is the dilution rate. So dilution is equals to the F by V. F is the flow rate, means how much amount of substrate is going inside, by the volume of the total reactor. So this is 0.3. And the product formed is growth associated, means the production of the product is having a close correlation with the production of the biomass. So here if it is the growth pattern of the biomass of the cell, then the production of the product will replicate it, and depending on that the product will be produced. So that is a association with the yield of that product 0.2 gram per gram for the presence of the biomass. What does that mean? The product yield is 0.2. That means if the 1 gram of biomass is present there, then it will produce 0.2 gram of product. And in order to obtain productivity 1.2 gram per liter per hour, that is the productivity, means the rate of production. So you want to have 1.2 gram per liter. So the solution, in the solution per liter there will be 1.2 gram of the product, and you will obtain it within a 1 hour of the time. Thus it is the rate, the time is mentioned here. Now to get this 1.2 gram of the product, and from 1 gram of the biomass you are getting the 0.2 gram of the product. So to get 1.2 gram of the product, you have to have at least, like from 0.2 gram of the product is getting from the 1 gram. That means you need to have 6 gram of the biomass. And this 6 gram of the biomass will be utilized, and that will make the product. Here, that is strongly related with the, so the your need of the biomass will be 6 gram per liter per hour. That is the rate of change of biomass concentration, which is equal to the dx by dt. So here dx is the change of the biomass and dt is the rate, means dx. So like it should be 6 depending on the equation. So the 6, that means it is dx, means 6 gram per liter, that is the change of the concentration of the biomass, and it will be divided by 1 hour. Thus 6 gram per liter per hour is the rate of change of biomass concentration. Now we know from the equation, we know that dx by dt is equal to mu x, and here you are maintaining the culture in a steady state form. In the steady state, the d would be equal to the mu. So the dx by dt, you know the value of the dx by dt, that is 6, and the value of d is 0.3, and you want to know what is the x. X is the biomass concentration. Its unit is gram per liter. So from this equation, just determine the amount of x, that is 6 by 0.3. The unit would be gram per liter, and it will come as 20 grams per liter. So the answer is the fourth one. If you see this kind of question and you are not able to even, means if you think this one is the difficult for you, then you can just follow this rule, that is the productivity P is equal to the dilution into the concentration of the biomass into the product yield. So from there you can also get the value. It is 1.2, it is 0.3, and you have to determine that x, and this is 0.2. From this equation you also can get the x will be 20 gram 20 gram per liter at a constant power number. So what is the power number? Power number is a dimensionless quantity which is used to characterize the power consumption of bioreactors. Like if you take the NP as the power number, then it is, there is the equation on it with the power consumption by the impeller divided by, that is the rho, density of the liquid, and thereafter the RPM, the, like that is the impeller speed, that is the n should be in a cube form, and the last one is the d to the power 5, that is the diameter of the impeller, and it is the unitless one. It is the power that is consumed by the impeller when the impeller is ongoing, how much power it is taking. So its unit is watt, and rho, it is the fluid density. Density means the kg per meter cube. It's weight by volume is its unit, and the n, it is the RPM, the tip speed, RPM, and D diameter, it is in meter. Now, depending on the question, it is saying doubling the impelling diameter. So you have kept this term constant and you are doubling the impelling diameter. If you are doubling this one and while having the steering speed and having this thing. So for the first case, if we take the N1 and D1, that is the RPM and diameter as N1 and D1. So the next case, the doubling the impelling diameter. So diameter, the D2 would be equal to 2 into D1, and then while having the steering speed, so steering speed N2 will be the N1 by 2. Now if we take the equation for the first one, for the first impeller and for the second impeller, then we will get, if we are taking that thing, that as a constant, the power number, and now we will get, so we have to determine what will happen with this power, the power consumption. So how it will change the power consumption, we have to determine that. So here the first one, it is the P1 by rho will stay constant because we are not changing the liquid, and this is the N1 cube, and this is the D1 to the power 5, which will be equal to the P2 by rho into cube and T to the power 5. Here you can write the P2 is equals to, rho will be cancelled out. This thing is equals to N2 is equals to N1 by 2, means N1 by 2 to the power cube, N1 to the power cube by 2 to the power cube into D2 means 2D, means 2 to the power 5, and D1 to the power 5. Thus it will be, we take it here, and it will be then P1 by P2 equals to N1 cube into D1 to the power 5 divided by, that is N1 to the power cube into D1 to the power 5 into, that is 2 to the power 5 by 2 to the power 3, that means into 2 to the power 2. Thus it will be cancelled out, and then it will be the fourth times of the P1. The P2 will be 4 times of the P1. So here in the option, the quadruple the power consumption. So the power consumption will be quadrupled. So power consumption will be higher in that case if you are modulating the speed and the diameter in such a way. Reduce the maximum shear rate in your reactor, that is via the impeller tip speed. To do this kind of questions, you just have to memorize some kind of equations. Like here, for the shear rate, there is an equation, that is the y. If we take the shear rate as y, then it will be equal to the Vt by the T by 2 is T. And this Vt is the tip speed. So you are changing the shear rate depending on the impeller tip speed. So this equation is the relation. This equation shows the relation between the tip speed and the shear rate. So the tip speed, right, its unit will be meter per second, and that is the d by 2. That is the diameter of the impeller, and its unit is meter. Actually, you are taking the radius. You wish to reduce the maximum shear rate. So that is the shear rate, and the shear rate is having a inversely proportional relation with d by 2. If the d by 2 get increased, then the y will be reduced down. So you have to increase the diameter of the impeller. So increase the diameter. Okay. It is saying about the reduce the diameter. It is saying about the reduce the diameter. So increase the diameter will be the our chosen option. And there we have to see its activity with the RPM. Anyway, we know the first one is the answer. So now you have to know another equation that shows the relation between the that is the power and the RPM of the impeller. So there is the equation that is this is the power consumed by the impeller, and it will be equal to the n to the power cube and n to the power 5, where n is the impeller speed. You will take it as the RPM, and d is the diameter of the impeller. So it is saying, so without changing the power consumption, so the power has directly proportional relation with n to the power cube and d to the power 5. So here we have seen, to reduce the shear rate, we have increased the the diameter. So if we have increased the diameter, then we have to reduce the RPM. So the speed we have to reduce. So we have to reduce the RPM and increase the diameter. That is the answer. For bench and plastic, that means this one. And for the pseudoplastic liquids, you have to determine the apparent viscosity. So in the graph, you can't see the term viscosity. So at first we have to know the equation. Again, we have to know the equation of the viscosity. That the viscosity equation is dependent on the shear stress. It is the stress by shear force or shear rate. So that is the force. Now see, in the graph, the shear rate via the y-axis and via the x-axis, you can see the shear stress. And in the Newtonian fluids, so this one is the only the Newtonian fluid, and the rest are non-Newtonian fluids. So in the Newtonian fluid, if you are inducing the shear rate, if you are increasing the rate, the shear stress will also getting increased in an exponential way. That means the stress by shear force, that ratio is staying constant for every cases. So here this is the shear rate and this is the shear stress, and here also this is the shear rate and this is shear stress. The values will be changed, but the ratio will remain constant. So this for this kind of fluids, for the Newtonian fluids, so as example you can say the water, so its viscosity is nearly to the constant. And the next one is the pseudoplastic. So after a certain production of the shear rate, after a certain shear rate like this, after that it is reaching the plateau. That means it is getting saturated. So however you are giving the shear rate, you are giving the force on it, but it is not able to produce the or get the shear stress. That means after a certain period of time, the shear rate is, that is a force, the shear force is, you are producing it, it is high, but shear stress will stay constant because it has reached the saturation level. Thus the viscosity will go down. And the same thing is also happening for the Brigham plastics. So initially it will be increased and thereafter it will be reaching a plateau, the saturation, the same thing like the pseudoplastic. So that is the, like, you are giving the stress force, and it is getting the dilated. The viscosity is going down. Can you give some example? As a pseudoplastic, you can give the example of the toothpaste. So when it is inside the tube, it stays in a solid form, nearly solid form. Unless or until you are giving the force on it, it will not show the liquid property. That means when you are producing the shear rate, when you are giving the force on it, it will lose its viscosity. And in the initial case, that's the same thing is happening for the Benjamin plastic. But it is a little bit different because in the normal case, when the shear rate, means the shear force, is too low, still in that case the Benjamin plastic is showing very high amount of the shear stress relative to the pseudoplastic. That means when there is no stress, or the no that means when there is no shear rate, or the no force has been produced, has been applied on them, at that time the pseudoplastic will show relatively less amount of viscosity, whereas the Benjamin plastic will have very high amount of viscosity even when the shear rate or force is very low. Because here you can see for the Benjamin plastic, the shear stress is too high and the shear rate is too low, whereas the same case, the shear rate and shear stress both are low in the case of pseudoplastic. And as an example of the Benjamin plastic, you can take like the mercury. So that kind of things are forcefully you are dilating. If you are giving the force, that things will be dilated. And the opposite thing happens for, it is the dilatant. If you are giving the force, then it will be more, like the viscosity will increase, like the solution of the starch. If you are having a concentrated starch solution, if you are producing the more shear force on it, then it will, like, it will gain some, like, the viscosity. So that is the dilatant. That is the only opposite, totally opposite of the pseudoplastic. So that will be the shear thickening. You are giving the shear stress, you are giving the shear force to make them thick. That is the shear thickening. So this kind of thinking, that kind of, if in the fermenter you are using the Newtonian fluid, then there is no problem. But if you are using some non-Newtonian fluids, then you also should know about that. Is that the dilatant or the pseudoplastic? Depending on that, you will regulate the shearing on the solution, on the liquid. If you are giving too much of pressure on the dilatant, that means they will be solidified. In the fermenter, you have kept a solution of, like, a solution of the starch, concentrated starch solution you have kept in the fermenter, and you are giving very high amount of, like, the shear force. That means it will be solidified. The viscosity will go very high, and thus in that way. So when you are pouring inside the fermenter, it was liquid, but inside it is acting as a solid, a high viscous media. So that means the mixing and everything will be, like, nothing will be proper in that case. So you have to optimize every kind of parameters for non-Newtonian fluids. That's a relatively tough thing. And thus, this is the property of the rheology, the fluid's rheology property, that deals with the, like, the fluidity, like the viscosity, this kind of things. So it comes under the rheology of the solution. Now the option 2, decrease with increase in the shear force will be the answer. So we have reached the end of our today's session. If you are having any kind of suggestions or any kind of problem, any kind of difficulty, you just openly can text us in the description box. We will meet in the next video.